Everyone, welcome to Seismic Data Processing course. In the previous lecture we talked about the vertical and horizontal resolution. So in today's lecture we give more examples so it will be easy for you to understand. So we have the well log. The well logs to measure the physical rock properties like density, porosity, saturation, but these only their vertical resolution is very fine, like around 1 meter. So the vertical resolution that we get from the well log is only 1 meter, and within the well log we have the depth of investigations. Depth of investigation is different from the lateral resolution. It's like radial distance, the distance that adjacent the well bore. So the maximum we can get from 1 to 2 meter for the deep restivity. This is the maximum depth of investigation. We also have the VSP, the resolution around 5 meter. So vertical seismic profile, VSP, the data is collected by placing receivers in the borehole. So we put the receiver on the borehole and the maximum vertical resolution that we get is around 5 meter. But for seismic resolution, we have from 15 to 50 meter, but this is depend on the velocity and the frequency. And from the velocity, velocity divided by frequency, we can get the lambda, the wavelength. So the wavelength is the most important in here. So wavelength divided by 4, so any thin layers, any bed layer is thinner like lambda divided by 4, we cannot detect these thin changes. So if you have, for example, in here we have this the reservoir, we can get this the high wavelength, but if we have a wavelength is lower than lambda divided by 4, so these small changes of thin bed we cannot get the changes within thin bed because it will be reflected and overlapped with the thicker layers. So the reservoir thickness, if a reservoir is thinner than a seismic resolution, for example 10 meter, and we have the minimum is 15 to 50, for the minimum is 15, so seismic data might not resolve it clearly. It could merge with other reflections. So the lambda divided by 4, the wavelength divided by 4, as we talked in the previous lecture in more details, is the key to detect if we can get this thin layer or not. If any objects, any features below the lambda divided by 4, then we cannot get these reflections. These reflections will be mixed and overlap with the other layers. Zero threshold for vertical resolution. The resolution is determined by these 3 factors. If we need to get the lambda, the wavelength is equal to velocity dividing by frequency. So if we have very high frequency, that means we have very short lambda, and if we have very high frequency, that means this is the better resolution that we get, the better fine resolution. If we have very high speed, you will have very large lambda, and then we have very low frequency. If we have very low frequency, this means it will be very poor and a crosser resolution. So understanding these factors, we have the lambda equal to velocity divided by frequency. The frequency is the so how much cycles per second. We have, for example, 60. If we have frequency in here 50 frequency, that means we have 50 cycle per 1 second. And if we have higher frequency, that means we have very low lambda, for example here 10. So this is 50 frequency, it will be stretches in this 10 meter. But if we have 20 lambda, 20 frequency, and this is 20 frequency, it will be stretched with 62 very long lambda. So if we have very long lambda, that we have very low frequency and high speed. That's why this will be very long lambda, the resolution will be very bad. But within the high lambda, that means this wave can travel for a long distance, but within the low lambda, that means the wave can travel faster within the shallower depth. So the higher frequency, the shorter the wavelength, the better the resolution. But the problem with high frequency cannot travel deeper because it will be absorbed from the rock particles. That's why we need both the high frequency and also the low frequency, because low frequency can travel for a longer depth, and this is helpful when we have for deeper investigation. I give some examples. So if we have the velocity is 2400 meter per second and the frequency is 4 hertz. 4 hertz mean we have 40 cycles per 1 second. So 30 cycles per 1 second, that means if we have high frequency, that means we have very low lambda. So 2400 meter per second divided by 40 hertz, we have the lambda is 60 meter. If we have the lambda is 60 meter, so the vertical resolution is lambda divided by 4. 60 divided by 4, we have 15 meter. What does that mean? So the lowest feature that we can detect the reflections is 15 meter. Anything below the 15 meter, we cannot see these reflections. It will be overlap with the lower and upper layers. Anything within the 50 meter, so and above, we can detect the reflections between the two layers. So the thinner layers will appear as one reflections if they have lower than 15 meter. So the key points: higher frequency, better resolution; low frequency, poorer resolution but deeper penetration. We have another example. If the velocity is 2000 meter per second and the frequency is 50 hertz, so we have high frequency, that means we will have low lambda. These 15 hertz, each wave cycle, one up and down, stretches across 40 meter. So all these cycles per second, because the hertz is a cycle per second, so these the cycles per second, the frequency, it will be stretched within the 40 meter lambda, because the lambda is the distance between peak and peak, or a trough to trough, within one full cycle. So this it will be lambda is 40 meter, that means one full cycle it will be stretches within 40 meter. So 40 meter, this it take 40 meter to complete one full cycle. One full cycle from up to down, up, down, this will be stretched within this 40 meter. So the vertical resolution is roughly lambda divided by 4. So we have 40 divided by 4, that means 10 meter. So that means the smallest layer thickness we can distinguish is about 10 meter. So 10 meter, we can see the reflections between two layers. Anything below, we cannot see this thin layer, the below 10 meter. So it depends on the velocity and depend on the frequency. So in here, just illustration of what is the high resolution and the low resolution. So if we high frequency, that means we have less depth of penetration, because the high frequency it will be absorbed from the rock particles. But if we have low frequency, we have very deep depth of penetration, because we'll go for a deeper. Okay, and if you have high frequency, we use the high frequency for high resolution, we get the high resolution. If we have high frequency by hertz, 80 to 100 meter, very high resolution, we can detect the difference, the reflections or between the layers very easy. But if we have low resolution, it will be very hard, but it will also be helpful to detect the deeper. So this is all you need to know about the seismic resolution. And in next videos, we'll start learning how to migrate our data, how to collect our data from field into the lab, into computer step by step. So thank you for watching, and see you in the next video.